So if you go to, we will talk about this in detail later. For a simple DBMS like SQL Server, you can also specify what kind of access path you are expecting for a specific query. For example, so here you can guide query processing and execution and query execution plan. So we will talk about plan guides. You can either specify explicitly what kind of plan you want to choose for query processing, or as we mentioned before, the DBMS will choose the shortest access path to execute the query. So this is basically called selectivity. So here we will see that what kind of access plan guide we can have. We are just briefly introducing the theory behind all of these execution plans. We talked about this, right? We finished this. We talked about different types of queries. Did we? So, one of the very frequent queries, or one of the important part of a query in the database is usually a join. So, computing a join is playing an important role in the execution cost of
selectivity.
what?
Whether we decide or the computer decides.
So, okay. So we haven't decided. We haven't explained selectivity, right? We either selectivity is basically the number of the pages required to be retrieved for. We talked about this, right?
I have a doubt. Whether we decide what in what.
Both of them is fine. You know, either you can decide it if you explicitly say to the data DBMS that for this, for example, this type of join, go and load this table first. Then the DBMS will go and choose your access path. Okay. Otherwise, if you do not specify anything, DBMS will go and use its own DBMS.
Where to specify?
What?
In SQL.
In the SQL Server, in the plan guides. Here in the plan guides, for each database in the programmability, you can tell to the SQL Server what it should do when it faces one specific query or one specific join. Either it can go through the statistics, it goes and collects you can see the statistics of the queries somewhere. I just don't remember where it was, but the SQL Server can show you graphs about how queries are frequently called and what is the statistics of each query, and also statistics of indexes. So both of them are fine, and you can see that. I don't remember, but SQL Server has a very nice GUI to show all of the statistics to you, and you can also also use those statistics based on what you learned here about deciding what kind of selectivity path. So, as we mentioned, if several access paths are existing, then BBMS chooses the lowest selectivity. And we talked about this, right? Size of the molecules. We didn't talk about computing joins, did we?
No.
Okay, so joins are very frequent. You saw that we had several nested joins in all of our queries. For example, potentially having 5 or 6 joins in a query is very, very usual and frequently happening for the DBMS. So addressing this problem is very important to the DBMS. So basically, in order to compute the join, for example, between table R and S, where we are trying to join these tables based on attribute A from table R and attribute B from relation S, the simplest way of computing this join is writing simple block nested loops, right? So if you want to write this program in Java, what you are doing is you will have a nested blocks of loops. One loop is iterating inside of the other loop, and basically, first of all, you try to load one page from relationship R, and then you go over relationship S, and you try to load each page of relationship S to the memory, and then compute and see if any records are matching the join or not. If they are matching the join, then you have to keep a buffer and add that record to the buffer, and finally output the buffer. So what is the cost of this kind of processing? So hold on. Do we use any kind of indexes here?
No.
So this is the simplest way. We do not use any indexes, and sorry. So we will see what is the effect of adding indexes on each of these attributes. For example, if attribute A is indexed or attribute B is indexed, and what kind of index they can have, they can improve the join. So for the simplest case, what is the cost of joining? The cost is number of the basically number of beta R is the number of the pages of relationship R, and beta S is the number of the pages in relationship S. So the cost is, you have to first for each row, for each page of R, you have to load the page R to the memory in this case, and then for each page, to the number of the pages, you have to load pages of S. So it will be beta R add plus beta R plus beta R times beta S plus cost of the outputting final result. Why is this important? Cost of outputting final result. Suppose that you have a joint relationship and the output is very large. Then the number of times you have to write on the disk will be very high. But if you choose a result of join very small, the number of the output will be very small. So then you can, when you are writing a query, you can have this rule in your mind that first try compute the smallest join first. Okay. So suppose that you are writing a multi-step sort procedure. Okay, hold on. Sorry for this interruption. I'm very excited that I'm using this software. So suppose that you are you are writing a stored procedure with different types of relationship, or you are writing a stored procedure and you call different functions, okay? And each function uses a join, okay? So when you want to call functions, you can keep in your mind that the smallest join should be, can keep it at first, because the cost will be minimized, right? So let me show you. Do we have any join here? Okay, so suppose that you have this stored procedure, and before this step, you have another step that computes some result in a temporary table. Okay, if that temporary table is very big, then removing and adding that temporary table to memory will cost a lot of time. Okay, so when you are writing a stored procedure and you have different selects, and each select is using a temporary table you are creating. For example, you declare, for example, you declare someone as a table, and you put different columns for this, like for example this column, and this table is used to collect some information between different type of the source and selects. Okay, you create this table, then you compute the result, and then you send the table to another join and ask another result. If you are taking this, then since the size of this table, here you can see that the size of this output matters for the rest of the execution, then you need to consider this temporary table as small as possible. Okay, we will see this in the stored procedure, and we'll see why some stored procedure can be more efficient than the other one. So suppose that we have two relationship RNAs, but both of them are containing 1,000 pages. So the cost will be 1,000 plus 1 million. Okay. So if beta R is much less than beta S, then it's better to have the first relationship, the smallest relationship, as the outer loop. Why? Why? DBMS chooses the smallest relationship as the outer loop.
The outer loop will look for less times.
Right, because this number will be decreased, right? This number you have here. Use the technology. This number will be less, and the cost of the query will be less. So, in practice, if your memory can contain m number of pages, okay, then in reality the cost of the execution of the query will be beta R plus beta R by m minus 2 times beta S cost of output final result. Why? Because you read m minus 2 number of pages from beta R. You do not put them in the disk until you scan the whole beta S. And if you assign one beta S to each of those pages, then the result will be more efficient. So this is one example of execution of the multiple block nested loops. Suppose that you have a relationship R, which is now 4 pages, and relationship S, which has 2 pages. So you load 2 pages from R, and then you start loading pages from the S and outputting the results. What is the cost of this execution?
Can I say one more?
You want to see the formula?
Question है.
What is the cost of the execution of this block nested loop for relationship R and S? What is the cost of join?
R by S.
I cannot hear you. What was that, Krishna?
It will be R by S.
R plus
The
R
size of
times.
the R is, beta R is
4.
4. 4 plus
2 into 4 into
4 plus 4 divided by
4 plus
4 plus
4.
divided
plus
by
2.
How many times do we need to load S?
2 times.
Again 4 times.
Why?
For each block in R, we have to load S. Each.
No, why 4 times? Decided to class. What's the cost of this? Krishna is saying that for first time I will load these 2, load one of them, and just then compute this. Suppose that we have 2 output pages, 2 output pages. Okay. So first we load this. How many loads? How many page reads? How many page falls?
3.
No, 2 of them. One of them.
2 and 1.
Yeah, 3. Then we will have one more block read, one more page read for the second one, plus 1. Okay? Then we will have the second part. Again, we will load 2. Then we will read the first part. And then we will read the second part of S. How many times? 3. 3.
8.
8. Is that true? Is that efficient? Why, Fanindra?
Looks like not efficient.
Why is not efficient? Okay, Fanindra has a better suggestion. Back row, do you have any better suggestions? Can we decrease the number of the reads? We read the first 2, then one of this S. We went through output. Then we read the second block page of the S. We went through an output. Okay, sorry. We have 10 page files. Why?
2 outputs.
2 outputs, right? 2 times this buffer gets filled and you have to output. Okay, so it's 10 times. So one of people at the back row was telling that it's not efficient. One more efficient algorithm is when you go over this and you load this one. 2 page falls for reading these 2 pages. One is for reading the first page. The other one is reading for the second page of the S. then we need to read these two pages again. Then we need to read these two pages again, right? I wish I wrote it over there, right? Okay. So, two page faults. Then starting from from this one or this one. If I'm sure that if this time I load this one, I can go over this, right? So I don't need to reload the one page of the S. We go and run the second part of R with the second page of S. Go and output. Then I go back and roll the first one. Okay, plus 2 as the output.
9.
9. One was less because
By using the already loaded page.
already loaded pages. So okay. I have a very difficult time. Yes, Peter, we could have 9 page faults. So now suppose that we are using index on one of the rows, okay? So suppose that we have index on one of the tables. We have index on S on attribute B, which is contributed to an attribute B, which is contributed to join here. You can see that, right? B is here. So S is indexed on B, then what we can do is we need to read relationship R. For each row in the R, we can use the index. Okay? And then with the index, we need to retrieve the values and just output. So here, index is the omega. The omega is the average cost of retrieving rows in the all rows in S matching that join condition, right? So this is very efficient when
Low number of rows.
number of rows in S is very small, right? Why? Because you are using very small index, which is maybe loaded already in your memory, and you do not have any page fault for reading index from the disk. Okay? Then a few numbers of the rows from S should be retrieved. So since you are not going to disk for a lot of time, then you just need to select those indexes that is index entries that is matching the beta R, then go and find them and put them output. Or the index, if the index is clustered. If the index is clustered, it's easier. Why?
The index is
Why if the index is clustered?
then it will check with the verify with the index directly itself. So no need to verify with the name again, the B again.
No, because when you load a page, okay, so you find the row, you have the beta R. You retrieve the beta R, the relationship in R, okay. You find the attribute, you go to the index and find the attribute, okay. So when you want to retrieve the row from the index, since the index is clustered, it means that the rows and the physical space is also sorted based on the B, right? So if you find something close to this one, to the current R, then it's probably, if you already loaded the page, then it will be in that page, right? Because it's sorted. Otherwise, if it's not sorted, you find one row from the index the row could be at the end of the file. You have to go and retrieve that page from the end of the file. The second row will be from the beginning. The rows are randomly distributed over the files. But when it is ordered, then you are going through, when you are going through and you're loading pages, then when you are advancing here, the next indexing tree must probably currently in the memory. So, sorry. This was the algorithm for using index. The other way of computing join is using merge. Okay, so in order to compute join as a merge operation, as a side operation around the merge, what you are supposed to do is the first action, you have to sort relationship R on the attribute A. Okay. Then you have to sort relationship S on attribute B. Okay? Then you start to merge these two relationships, but merge is not like a merge sort. What do we mean by merge? We mean that when these are sorted, then each page of rows are sorted, and when you retrieve one page, and you retrieve this corresponding page from relationship R and S, then the next pages will be consecutive to these pages, okay? So you start from the beginning. You start from the beginning, load the page, and go on inside of the memory. You try to merge, and as soon as you find one row matching, then you put it output. And you advance these two relationships all together. Okay, so for example, here suppose that we have relationship R and S. Relationship R has these two attributes D and A, and S has these two attributes B and E. Okay, and we want to merge on attribute A and B. Okay, so what we are doing is we want to use attribute A and B to join these two relationships. So you can see here that the relationship is sorted based on attribute A and B. Okay, so we start from the beginning. For each of the relationship rows in the attribute in the relationship R, you check if the corresponding row is existing in relationship S. And as much as you can go through, you advance, and for each of those relationships that has the same value for attribute A, you will go through a small space and see if there are existing some rows in relationship S that matches this attribute. Then you put this output. So here you can see that we have two rows with value P for A, two rows with value P for B. How many rows we should put in the output?
4.
4. You can see that these 4 rows with the same attribute. So you have to repeat it. So what is the cost of the merge sort merge join? Suppose that we have beta R pages for relationship R and beta S relationship. Beta R pages for relationship R and beta S pages for relationship S. So the cost of join, the cost of sorting, merge join sort is beta R. We read about this, right? You remember? Well, we read about sorting two relationships. So we can sort these two relationships if we have m number of pages available in the memory. If the capacity of memory is equal to m number of pages, the cost of merge sort will be beta r to beta r log beta r to the base of m minus 1, and similarly for the beta s. So this is the cost of sorting. So what is the cost of merging? What is the cost of merging?
Two into log m.
Hmm?
2 into log m base.
First of all, when you are merging the sort, okay, if you do not utilize the whole memory space for sorting just one relationship and just go over different relationship, okay, for the last step you can do the merge of all of those relationships in order to sort together with join, right? Is that true or not? Suppose that you are doing a merge sort on a relationship, okay? What is the last step of that merge sort?
Merge.
Merging some rows, right? When you are merging some rows, you are loading some pages from those rows and you are trying to match and output the smallest record, right? Suppose that you are merging some rows for relationship R. If you have some of them in the memory, you have some rows in relationship S. You have some of them in the memory. Okay. When you are merging, you can do comparison for the join while you are merging, right? So you don't need for the merge sort when you are creating the final result. You don't need to create the final result on the disk. If you can put the final result, final sorted relationship on the disk, but while you are merging, you can also join. So it doesn't have any cost. So the other part of the cost is suppose that you have two relationships.
Professor,
Yes.
why it not have any cost?
It doesn't have any cost in addition to this merge.
We will take 100 records, a chunk is 20 records. We will have 20 records into the memory and we sorted and we measured on based on them. But in the other 40 records, there is some records you can able to add into these things.
No, the last step of merge sort. What is the last step of merge sort? Merging, right? You have, for example, m number of pages. Sorry. You have n rows that are sorted, okay, and n is less than m, the size of the memory. You have n rows to sorted. You want to merge them and create a sorted relationship, okay? You read n pages to the memory, okay? And for each of those pages, you compare which one is the minimum. And the minimum one will be go to the output, okay? Suppose that you are doing the same thing for the relationship R and S at the same time.
But think we have more data, so we cannot load everything into the memory.
Yeah,
We will get first
we
chunk.
can assume, okay.
Some chunk
Yes,
of data.
you are right.
The other chunk is having.
We assume that we can load all of them in the memory. If you cannot load all of them in the memory, then if this n is very big, you cannot do that, right?
Then directly you cannot put out into the.
You have to make this n as small as possible that 2n can be fitted in the memory, right? And 2n plus 1 output, you have to output also. But you don't need to output all of the records. Why? Because you don't need, if you don't need this sort of relationships, why are you sorting, just for the purpose of join. As soon as you find a match, then you put the match output. Then the output will be much, much smaller, right? So the other cost is depending on the size of the A equal to C. What does it mean? If I go to the previous page, you can see that, for example, the relationship R, if the size of the part that has a value of A equal to P is very big, then you cannot fit all of that into the memory, right? So in order to, as the here, we saw that here the number of the records was R equal R, where A is equal to P multiplied to S, B equal to what? P. If this R, this part of R is very big, then you cannot do this Cartesian join all of it in the memory. So you will have some page faults. So the second part of the cost depends on the size of this relationship. So what did I do? So what is the result? What is the implication? Suppose that you have two tables. One is for the students, one is for transcript. Okay? And in the transcript table for each student you have a lot of grades. For example, the student was not very good and he failed a lot of times. So if the part that for each student you are loading the student, okay? For example, suppose that Farida is a very good student, but suppose that he was not a very good student and he would pass each course tons of times, like he took every course 20 times. So then the number of the rows in the transcript table will be 20 times. 20 multiply. How many courses do you pass and do you take in the program?
11 courses.
11 multiplied to 10. He has 110 records in the transcript table. Okay. Suppose that your memory is smaller than 110 records.
220.
What?
220.
What?
20 times.
Oh, you're passing each course 20 times?
Yeah. If he wants to pass
Okay.
20 times.
Suppose that he attempts each course for 20 times. How many records he has in the transcript table? 220. Suppose that your memory is smaller than 220. What happens is, so when you are computing this part of the join, you will have a lot of page fault, specifically for those records. It has a lot of. So the only parameter is not the size of the tables, but also if the repeated number of the records. Okay, when you are using merge joins. So when you, for example, now you got the idea. When you have a table where records are repeated like that, and you have this join, and by default the DBMS thinks that merge join is very fast because you see that the cost of merge join is much less than loop join. But you can say but DBMS will go and choose a merge join, sort merge join, right? But you have to explicitly tell to the DBMS, sir, do not use this type of strategy. Okay, because I know that I have bad students that are attempting each course several times, and the course cannot be fitted in the memory, for example. And the final cost is cost of outputting the final result depending on the size of the result. So okay, then the last part, not the last, we have the A plus 3. Okay, the last algorithm for join is using hash. It's very efficient. So what are you doing in the hash join? You define a hash function or relationship or based on hash value, the parameter of the hash function should be this type of a class. The last part, last one. What is the parameter for the hash function? For relationship or which attributes are? I thought that you know the answer and you were talking about the answer. Okay. So the other part of the class. What is the parameter for the hash function?
Yeah.
A or B.
A from R. B from
What was it?
A or
A.
No, for the relationship R.
A.
R is A,
Is A.
right? The hash parameter is A, attribute A. Then you have to hash the other relationship based on attribute
B.
B, and then
Matching records calculate.
match them when you are hashing it, when they are when they are falling into same bucket. It means that the values for those records are same. Then you just put output. So the same step is the first step is hashing R on A and hashing S on B, and see if they are falling into the same bucket. If they are falling into the same bucket, then we need to just read that bucket and retrieve the records. What is the cost? 3 beta R plus beta S plus cost of the output final. Much less than what? Much less than sort, merge, sort, merge, join, and also what was this? Sorry, nested loops. Okay. Just let me go over star joins. I'll explain the star joins more later. So the other type of frequently happening join is the star joins, right? We talked about. So let me show an example. Yeah, I don't have any example now for star joins, but the star joins are those joins that there is one relationship that dominates the join. It means that other relationships are trying to match their records with some specific parts, some specific attributes of that relationship. Okay? So these are called the star joins. Okay, here we have a very good example. Here in this database schema, you can see that if you want to compute different types of reports, then we need to have a star join usually on transcript. Why? Because most of the tables have common fields, common attributes with transcript. Okay. You had the midterm exam on Thursday. Give me this answer. When you are drawing in transcript, Let me write a question for you. You learned about or S T U. What is the answer to this question? You had this midterm on Thursday, right? And everyone is fresh.
Entity image.
We're betting on entity. We're betting on entity. Kada switch. Kada vendor money. J. Just. You decide about your policy. Relationship or entity. Which one? You cannot choose both of them. Barbie? What was it? What? You change your mind? You have to bring a good reason. Give me the attendance sheet, please. Oh, where is the attendance sheet? Yeah. 1 minute more to get the answer. Anusha. Anusha. Where is she? Anusha, what is the reason? What's your idea? Relationship or entity? Relationship, why? Because relationships are those part of ERD that are mapped to tables, but they are used to relate different tables, different entities. So they have the most common attributes with other entities other than relationship entities. You understand what I'm saying? Relationships are those part of the ERDs that are trying to connect entities, right? In order to connect entities, what do you need? Common attributes. So they are those tables, those relations in the database, those tables in the database, where need to have common attributes with different parts of the ERD. So relationships are those. So here between all of these tables, R, S, T, U, and W, table R was the table created because of a relationship. Because it is a center of a joint, a center of a star joint. It needs to have a lot of common attribute with other tables. Then it should have been a relationship instead of an entity. So it was a very good question. So now if I give you a ERD, if I give you 4 ERDs, and if I ask you for the average queries for these ERDs, which one needs to be more efficient on joins? You have to see which one has more relationship and star joins are happening in the relationships rather than 2 entities. And then you can see and you can guess, right? Class is over.